electricity, 95% of those people being in sub-Saharan Africa and rural Asia. And it's quite interesting because the lack of access to electricity and energy is one of the most prominent things keeping people in a cycle of poverty, but it's one of the few that's rarely talked about. Energy and electricity affects things like healthcare, automation, the ability to use mobile phones and applications, and education. And part of the reason why it's hard to get electricity and energy to lots of these places across the world is because currently the infrastructure is very capital heavy, there's a lot of wires, and sometimes it's even hard to get these really big transformers and cables to maybe places with rough terrain. So that's why I'm so excited to be talking with you guys about wireless electricity today. I've been looking into it for a full 2 days, so hopefully you guys learned something interesting. So today I'll be talking about 3 types of wireless electricity: magnetic induction, resonant charging, and radio frequency charging. They're all really cool and they serve different purposes. As you can see, they have different regions at which they can supply their electricity. They have different pros and cons, but they're pretty much the 3 big players in the space. So let's start off first with magnetic induction. So here's a fact. If you have a current in a wire, and a current just means electrons are flowing through, there's electricity, there will be a magnetic field. So it got scientists wondering, what if we start with having a magnetic field? Will it induce the current? Will there be like electricity that is created even though it's not plugged into a battery or something like that? So lots of scientists tried to do this, and they failed. It wasn't until Henry and Faraday that someone found something interesting. So if you just had to visualize how this setup might have looked like, it might have looked something like this. You have a coil carrying your electric current that is powered by a battery. So when you have the electrons swirling through here, it generates the magnetic field. And then you have another coil on the other side which is not plugged into a battery, but it's close enough so that the magnetic field can pass into that one, and you're trying to see if it can power or generate some sort of current. So Henry and Faraday found something really interesting at about the same time, even though they were working independently, and everyone was stuck. But they noticed something really interesting. That was, as soon as they started turning on and off the battery, at the last second, it would generate a quick spike in the other electric current that was not plugged in. So it got them wondering, and Faraday came up with his first thought hypothesis that only a changing magnetic field can induce an electromotive force current in a loop of wire. So electromotive force just means that the current is being induced and there is movement of electrons. So he came up with these really fancy equations with the help of a guy named Lenz, and pretty much they found that electromotive force is the change in magnetic flux over the change in time. So if we go a little bit deeper, magnetic flux is just the measuring of magnetic field running through the loop, and if you look at this equation, there are different variables that are plugged in that look at things like the strength, the number of loops, and the area of loops, and the angles. So when they were looking at this negative proportion, Faraday updated his law to now being like a change in magnetic field or a change in area or angle will induce an electromotive force in a loop of wire. So I thought this was super interesting, so I decided to build a really quick project to showcase my learning, and so I'll just play it for you guys now. But it essentially uses this idea, and I don't think there's sound, but I will just talk over it. So I'm not sure if you can see it, but it's there is sound. There is the wire the wire on the bottom is plugged into the battery, and then the receiver at the top is not. So I'll explain how it works without competing with my audio, but pretty much there's a battery that powers the first electric coil, and that's plugged into a transistor. So all the transistor does is starts and stops the current quickly. And this is me saying, well, that one doesn't really light up much. I want to make it light up more. So this is the second one. I'm not sure if you can see it, but it's a larger wire. It's a speaker wire. So this pretty much worked in the same way. It had the receiver, so that's the receiver. The receiver's not plugged into anything. It's just a loop of wire, and if you put it on top of the one that is plugged into the battery, the magnetic field will reach the receiver. And you can put a piece of paper in it, you can put a wall through it, you can put anything you want through it, and the magnetic field will go across. This one works the same way. There's a resistor and a transistor. And the transistor allows you to start and stop the current, to have the changing magnetic field in the bottom, and then your receiver at the top lets you collect the energy that you created. So I thought that was pretty cool. But it made obvious some really interesting problems that wireless electricity faces, in that it can't go very long distances, which is why resonant charging is super cool. So I'll just show you this quick video to explain it, because I think it makes a lot of sense. I don't think the audio will play, but we will try. Maybe it will.
And it's a size and distance phenomenon, i.e. the size of this and the size of this determine how far you can go. That makes sense. You can't go forever without making it bigger, right? But it turns out that actually you don't have to make either of these objects bigger if you make another object in the space bigger. So you can create a passive object, that's what this is, a repeater, okay, which is resonant at the same frequency, but doesn't use energy. It just lets it hop through. So you'll see as I raise this resonator to the point where it just goes down. So it's out now, right? You can see just in that last yes. But now, if I place this object there, it hops through one and goes to the other. But now, look how far we can start to go. I mean, we're probably a couple feet at this point, exactly, away from the source of the electricity. That's amazing. So those four things are what electricity is all about.
So I thought that was super cool. It pretty much allows you to extend the distance of your magnetic field to reach things that you thought you couldn't reach before. So resonant charging works by allowing you to have a passive repeater, and if it oscillates at the same frequency as the electric coil, then it can transfer the electricity over longer distances. So, for example, as you can see here, if you have more resonators and passive objects, you can extend the distance that you wish to go. So, I'm sure you're all wondering, what kind of objects can we use to allow electricity to go longer distances? And something really interesting is that everything has a frequency. So everything has a certain wavelength or frequency that it likes to oscillate at, if it has an electric current or things like that. So you can have these really fancy things that can be your passive amplifiers of sorts. But something really interesting was some smart people think that, what if you could just use the Earth? So there was this dude named Nikola Tesla, and he was like a pioneer in the fields of radio, X-rays. He was a super smart guy. And one of the things that he tried to work on was, what if we can use the Earth's frequency to be able to transfer this current everywhere, like propagate it across the globe? And using a receiver, then people could pick it up wherever they were without having to deal with cables or wires. So he was funded by JP Morgan, and this was how his tower was going to look like. He wanted to build a tower that had metal feet going straight into the Earth so that he could propagate and use the Earth's frequency almost as a giant wire. But he ran out of money, and then he died, so it didn't really work out. So it's still a question, will it work? Will there need to be technical advancements to make it happen? No one really knows, but the world progressed using wires, and here we are today. And the final one I want to talk about is radio frequency electricity charging. I think it's super interesting. It's what a lot of new companies are using because it shows a lot of potential. So the first step is you emit radio frequency waves. One of the ways people are doing it now is with antenna, because if you put an alternating current in an antenna, it emits electromagnetic fields, which can later be picked up by other things. And then step two is to take these electromagnetic fields that you have and convert them into electricity. And there's lots of fancy different ways to do this. And I was kind of skeptical at first. I was like, how is this possible? But I watched some YouTube videos, and as you can tell by their like to dislike ratio, they're actually legit. So that was really interesting to me. So now if we take a peek at the applications of wireless electricity, I think they're really interesting. Qualcomm, huge company in the infrastructure space, is working on parking spots that you can like park your electric car in and it charges, and even roads. So you can just be driving your electric car for forever because the road is powering your car. Apple bought a wireless electricity company. Even people are looking into for things like pacemakers or sensors in your body can be powered wirelessly. And this is a pretty cool video. That is, a company is going to power your entire house with one thing. So your phone doesn't have to be like on a charging pad. It can be in your hand.
The transmitter then computes the complex conjugate of all the incident waves and then transmits a higher power reflection of the beacon back to the receiver. All the individual power waves bounce off the same surfaces in the room and converge upon the receiver at a power level of up to 1 watt. This process is repeated 100 times per second to track moving receivers. Coda transmits power to mobile, wearable, and IoT devices with a user experience equivalent to mobile data, like Wi-Fi. A user simply moves around in the Coda environment while receiving power automatically. Coda transmits over room-sized distances.
So that one works in a pretty interesting way. They use the RF waves and they have a phone case which can transfer that into electricity to power whatever you would like. Some people even think that soon you might be able to like walk into a Starbucks and automatically have all your devices charging, and that would just be pretty cool. And it works the same with somewhat of the same waves as like Wi-Fi, so that's why a lot of people aren't too worried about the technological and health concerns. So I guess my next steps are looking at like intersections between wireless electricity and brain-computer interfaces, because if we choose to go down the path of having them being powered in some manner, that would be cool. And also publishing an article about the thing I built, which was pretty simple, but I thought it was really interesting and a fun way to learn about electronics and how to go to a hardware store and buy the parts that you need. So I guess overall, wireless electricity is really interesting. And with the technological advancements that our future will inevitably have, maybe we might live in a world where we can power the world with the earth. Thank you.